So now we're going to first review the steps for writing or drawing Lewis structures, and then we'll look at the Lewis structures and how we can use them for ionic compounds in predicting the chemical formulas or the formula unit, and then we'll also look at those for covalent compounds. So the first step is to sum the total number of valence electrons for each of the elements involved or in the formula. If we have a polyatomic ion involved, we will add 1 electron for each of the negative charges. If we have a positive polyatomic ion involved, we will subtract 1 electron for each of the positive charges. Now that we have the total number of valence electrons that are available to use in our structure, we're going to draw a skeletal structure of the compound and show that the atoms are bonded to each other. So some rules here, we're going to put the least electronegative element in the center. And we're calling that the central atom. We want to make the structure look symmetrical. And after we have linked all the atoms together with a bond, and this is obviously in a covalent compound, we'll subtract those electrons that were used in the bonds from the total number of available electrons. Okay. Next step is completing an octet for the terminal atoms. So remember, those are the atoms that are bonded to the central atom. Except for hydrogen, it will always be terminal, but it only forms 1 bond. So it only needs 2 electrons. It follows the duet rule. We will subtract the electrons used to give the terminal atoms an octet from the electrons that were remaining after step 2, and we'll do that before giving the central atom an octet. So if the remaining electrons can satisfy the octet rule for the central atom, we're good. But if there are not enough electrons to give the central atom an octet, we will form double or triple bonds on that central atom to satisfy that octet rule. So now we're going to look at using Lewis structures for ionic compounds to determine a formula unit. So we are given first sodium chloride. And while we can easily come up with the formula unit by another method, we can also use the Lewis structure. So we start by writing the Lewis symbols for each of the elements in that compound, ionic compound. And ion formation, if you recall, is driven by the stability that ion accomplishes when it has the electron configuration of a noble gas. So metal atoms give up electrons, non-metal atoms gain them. So for the formula unit of sodium chloride to form, the sodium atom gives up its electron to the chlorine atom. So we get the sodium ion and the chloride ion. And this is the correct Lewis structure for sodium chloride, which also gives us the formula unit, which is NaCl. So let's look at magnesium bromide, or maybe I should say the reaction of magnesium and bromine. So what is the formula of the compound, ionic compound, that forms when these two elements react with one another? So once again, we have the Lewis symbol for magnesium, 2 valence electrons, and the Lewis symbol for bromine with 7 valence electrons. Now in this case, magnesium wants to get rid of 2 electrons. Bromine only needs 1. So that means we're going to need another bromine atom to accept that second electron from magnesium. So the correct Lewis structure for this ionic compound is magnesium with a 2 plus central and the 2 bromines that are attracted to that plus 2 charge on either side. And then, of course, the formula unit, MgBr2. We'll do one more. And we are going to find the formula unit of the ionic compound. Move that down a little bit. That forms when aluminum reacts with bromine. So, aluminum is a type 3 metal, or a main group metal, 3A, sorry. It's not a type 3 metal. It's a 3 plus, forms a 3 plus ion. And it has 3 valence electrons. And once again, we have bromine with 7 valence electrons. Aluminum wants to give up 3 electrons, so that means we need a total of 3 bromine atoms, each of which will receive or accept 1 electron from aluminum. So the Lewis structure remember the brackets around the anion with the charge outside, arranged to show the attraction between those plus and minus charges. So the formula unit for this compound is AlBr3. All right, so now we're going to start drawing some Lewis structures for covalent compounds. So remember, ionic compounds have an ionic bond, which is not a chemical bond, but that electrostatic attraction between those ions. Covalent compounds have covalent bonds, which are electrons that are shared between two elements. And we're going to start with ammonia, okay, and follow the steps that I outlined on the first slide to draw this structure. So the first step then is totaling the number of valence electrons. We get 5 from nitrogen, and we have 3 hydrogens, so that's 3 times 1. So we have a total of 8 valence electrons to work with. It's very important to keep track of those electrons. So it's like accounting in your checkbook. You want to subtract money that you've spent. Here we subtract electrons that we've used, and so forth. Next, we want to draw that skeletal structure. Nitrogen is the first element in the formula. What else? Oh, yeah, first element in the formula, and it is the only, and there's only one, so that's going to be central. And we know that hydrogens have to be terminal because they form only one bond. So this is my skeletal structure, and I've already used 6 of the 8 available electrons. Each of those hydrogens are satisfied, but nitrogen only has 6 electrons, and it wants 8. It obeys the octet rule. And we have 2 left, so we can give that central atom, the last step in our process, the remaining 2 electrons. So now we've used all of our valence electrons, and this is the Lewis structure for ammonia. One lone pair or one non-bonding pair is located on that central atom, and that will make a difference when we are assigning polarities in the chapter 10 material. So let's now look at one of our polyatomic ions, chlorate. We'll go through the same process. We get 7 valence electrons from chlorine, and we have 3 oxygens, so that's going to be 3 times 6, and we have a negative charge, so we have to add 1 electron for that negative charge. So we have a total of 26 electrons that are available to draw this Lewis structure. Once again, first element in the formula, and it's the only one there is, so that's going to be central. And I don't know that I mentioned this when drawing ammonia, but we want to make this look symmetrical. I'm just going to put the O's around like this. We used 6 electrons. So now we have 20 electrons left. We're going to give the terminal atoms an octet first. So I give each oxygen 6 electrons. It only has 2 from that bond. So it has 3 lone pairs around each oxygen. And when I did that, I used 18 electrons. I have 2 left. Chlorine only has 6, so it needs 2 more. So I'm going to give a lone pair to the chlorine atom. Now, this is a polyatomic ion. It has a charge on it. When we draw the Lewis structures of polyatomic ions, we need to place brackets around them, and this goes for positive polyatomics as well as negatives with a charge outside. So now let's take a look at water. H2O. We have 2 times 1 for hydrogen, with 6 for oxygen, so we have 8 valence electrons. We have only 1 oxygen, and we know hydrogens have to be terminal. So I draw my skeletal structure, make it look symmetrical, and I used 4 electrons, so I have 4 left. Hydrogens are satisfied, they've got 2, satisfying that duet rule, but oxygen only has 4 and needs 4 more, which we have, so we will give 2 lone pairs to that oxygen atom, and we have used all of our valence electrons. Now we're going to take a look at another polyatomic ion, carbonate, CO3 2-. We have 4 valence electrons from carbon, 3 times 6 for oxygen, and we have to add 2 electrons for that negative charge. So our total number of valence electrons is 24. I have 1 carbon. I'm going to place it in the center. It is, oxygen is also more electronegative, and again, we want to make this look symmetrical. I used 6 electrons, so now I have 18 left. And I'm going to give, again, my terminal atoms an octet first. Each of these oxygens needs 6 electrons to satisfy that octet rule. And 3 times 6 is 18. So I've used all of my valence electrons. So carbon still needs 2 more electrons. So that means we have to form a double bond. So one of these oxygens is going to share a pair of electrons with carbon. So the Lewis structure for carbonate is this with brackets. Now, we'll come back to carbonate when we introduce another topic called resonance. And when we do that, we'll see that this double bond could have been formed by any one of these oxygens. But we'll come back to that later in this set of videos. Right now, we're going to move on to a few more examples, and we're going to look at carbon monoxide. We have carbon with 4 valence electrons, oxygen with 6, so we have 10 valence electrons. Now here we don't have a central atom, but we're just going to link carbon and oxygen with a bond. We use 2 electrons, so we have 8 left. Now here is another rule. We first give the more electronegative atom, which is oxygen, an octet first. So oxygen gets the octet first, use 6 electrons, so there are only 2 left, and I will give those to carbon. But we still have to satisfy the octet rule for carbon, and it needs 4 more electrons. So that means that oxygen is going to share 2 pairs of electrons, and we will have a triple bond. So the correct Lewis structure for carbon monoxide is this. Each element has a lone pair, and they are connected by a triple bond. Okay? Let's look at SO2. We have 6 from sulfur, 2 times 6 from oxygen, so we have 18 valence electrons. Sulfur will be central. Its oxygen is more electronegative, and we only have 1 sulfur. So link to the terminal oxygen atoms, we used 4 electrons, so we have 14 left. Following our steps, we'll give the terminal atoms an octet first. And when I do that, I use 12 electrons, 2 left, which go to sulfur. Oops. So I have 0 left. Each oxygen is satisfied, but sulfur only has 6 electrons, needs 2 more. So one of these oxygens will share a pair of electrons with that sulfur atom. And we'll see when we discuss resonance that, again, that double bond could have formed on either one of these oxygens. So again, we'll come back to that. So now we're going to talk about something called bond order. And basically this is the number of pairs of electrons that are shared between 2 atoms. So essentially what that means is the number of bonds between 2 atoms. And so this is pretty easy concept to grasp. Let's take this structure and we can look at, there are 2 types of bonds in this structure. There are carbon to hydrogen bonds, and the bond order here equals 1, because there's just a single bond. And then the second type of bond we have is the CC bond. And this bond order is also 1. If we look at this structure, now we have a CH bond, and of course that bond order remains the same, but we have a double bond. So we have a carbon double bond, so the bond order here equals 2. And then finally, we look at this structure. We still have that CH bond, where the bond order is 1, but now we have a carbon-carbon triple bond. So this bond order is 3. And why do we care about bond order? It tells us something about the strength of that bond. So as bond order increases, bond length decreases, and bond energy increases. Remember earlier in the introduction, we saw that as far as bond strength goes, single bond is weaker than a double bond, which is weaker than a triple bond. Now, there are some exceptions to the octet rule, and you are responsible for knowing these exceptions. The first one we're going to look at is beryllium. And the example here is BeH2. And beryllium only wants 4 electrons, or 2 bonds. Okay? So the exception here is beryllium is satisfied with 2 bonds, or only 4 electrons. Another exception, and these are incomplete octets, is boron. Boron has 3 valence electrons, and I failed to mention beryllium has only 2 valence electrons in its 2s subshell. Boron has 3 valence electrons, and therefore it only forms 3 bonds. Again, an incomplete octet. So it's satisfied with 3 bonds or 6 electrons. So beryllium and boron are happy with less than an octet. There are 2 other types of exceptions to the octet rule. One is odd electron molecules. And we need an even number of electrons to satisfy the octet rule. So if you've got an odd electron molecule, you can't satisfy the octet rule. And nitrogen monoxide is an example of this. Nitrogen has 5 electrons, oxygen 6, so we have 11 electrons. And the Lewis structure for NO is this. We give oxygen its octet, and nitrogen has an incomplete octet. These types of molecules are called radicals, and they are highly reactive. So this won't hang around very long. In fact, it would react with another NO molecule to form N2O2. Moving forward, the expanded octet. So once we hit n equals 3 on the periodic table, we introduce the D subshell. And those elements in row 3 then have an empty D subshell, which allows them to accommodate more than 8 electrons. And we'll talk more about this and look at how this happens, or it's hypothesized or predicted to happen in a little bit more detail. But sulfur is one of those atoms or elements that can accommodate an expanded octet. And here we have sulfur hexafluoride. So we have those 6 fluorine atoms surrounding that sulfur atom, who has 12 electrons, 6 bonds or 12 electrons. And we will see more examples of expanded octets in Chapter 10 when we discuss geometry. So we will be drawing more Lewis structures and adding the shape of those molecules to them. And so let's see, this is the end of this video. We'll be looking at resonance and formal charge next.